Missile technology has consistently evolved, each era marked by breakthroughs that redefine warfare. From the rudimentary rockets of the early 20th century to the sophisticated intercontinental ballistic missiles of the Cold War, the quest for speed, accuracy, and destructive power has been relentless. Today we stand at the cusp of a new era, the age of hypersonic weapons. Traveling at speeds exceeding Mach 5 or 5 times the speed of sound, these missiles represent a paradigm shift in military technology, promising to reshape the global balance of power. Among the leading contenders in this hypersonic race is Russia's M22 Zircon, a sea-launched cruise missile that has garnered significant attention for its purported capabilities. With its blistering speed, maneuverability, and ability to evade conventional defense systems, the Zircon embodies the disruptive potential of hypersonic technology. This essay delves into the technical intricacies of this missile, exploring its design, propulsion system, and strategic implications in the context of modern warfare. The Zircon missile, with a reported range of up to 1,000 kilometers, is designed for both land attack and anti-ship roles. Its compact size, estimated to be around 8 to 10 meters in length, enables deployment from a variety of platforms, including surface warships, submarines, and potentially even aircraft. This versatility, coupled with its hypersonic speed, makes it a formidable asset in any military arsenal. The missile's construction involves advanced materials capable of withstanding the extreme temperatures and pressures generated during hypersonic flight. Its outer shell is likely composed of heat-resistant composites and alloys designed to endure the intense heat generated by air friction at hypersonic speeds. This robust construction ensures the missile's structural integrity, allowing it to maintain its trajectory and deliver its payload accurately. Inside the Zircon's sleek frame lies a sophisticated guidance system, combining inertial navigation with satellite guidance for pinpoint accuracy. The missile is believed to have an advanced seeker head, possibly incorporating infrared or active radar homing, enabling it to lock onto targets with high precision, even at extreme speeds. This sophisticated guidance system, combined with its maneuverability, makes the Zircon incredibly difficult to intercept. Further enhancing its effectiveness is the missile's stealth capabilities. The Zircon's design incorporates features to minimize its radar signature, making it harder to detect and track. Its speed further complicates detection, as it reduces the time available for radar systems to acquire and lock onto the missile. These stealth characteristics contribute to the Zircon's survivability and increase its chances of penetrating enemy defenses. The Zircon's defining feature, its hypersonic speed, is achieved through a sophisticated propulsion system known as a scramjet engine. Unlike conventional jet engines that rely on rotating turbines to compress incoming air, scramjets utilize the missile's hypersonic speed to compress air for combustion. This allows the engine to operate efficiently at speeds exceeding Mach 5, propelling the Zircon to unprecedented velocities. The scramjet engine, often described as a flying stovepipe, operates on a simple yet powerful principle. As the missile travels at hypersonic speeds, air is rammed into the engine's intake, where it is compressed and mixed with fuel. The resulting mixture is ignited, creating a powerful thrust that propels the missile forward. This efficient combustion process allows the Zircon to achieve and sustain hypersonic speeds, making it a formidable weapon. The development of scramjet technology has been a significant breakthrough in propulsion engineering, paving the way for the realization of hypersonic flight. The Zircon scramjet engine, a testament to this technological advancement, enables it to reach speeds that were previously unattainable, revolutionizing missile technology and ushering in a new era of warfare. However, scramjets also present unique challenges. Their reliance on high speeds for efficient operation means they require an initial boost to reach operational velocity. This is typically achieved through a solid-fuel rocket booster, which propels the missile to supersonic speeds before the scramjet engine takes over. Once the scramjet ignites, the missile accelerates rapidly, reaching hypersonic speeds within seconds. Section 4. Unmatched speed and maneuverability. Zircon's defining traits. The Zircon's hypersonic speed, estimated to be around Mach 8 to 9, grants it several tactical advantages. It significantly reduces the time it takes to reach its target, compressing the time frame for enemy defenses to react. This speed also makes it incredibly difficult to intercept, as traditional missile defense systems are designed to counter projectiles traveling at much slower velocities. Adding to its evasiveness is the Zircon's maneuverability. Unlike ballistic missiles that follow a predictable parabolic trajectory, the Zircon is capable of performing complex maneuvers during flight. This allows it to evade defenses, change course mid-flight, and approach its target from unpredictable angles, making it a nightmare for defense systems. These characteristics, combined with its stealth capabilities, make the Zircon a highly survivable weapon. Its speed, maneuverability, and low radar signature provide it with multiple layers of defense penetration, increasing its chances of reaching its target successfully. This makes the Zircon a potent deterrent, capable of holding even heavily defended targets at risk. The combination of hypersonic speed and maneuverability represents a significant leap forward in missile technology. The Zircon, by embodying these traits, sets a new benchmark for missile performance, highlighting the disruptive potential of hypersonic weapons in modern warfare. Section 5. A New Era of Warfare. Strategic Implications of Hypersonic Technology. The development and deployment of hypersonic weapons, exemplified by the Zircon, have profound implications for strategic stability and global security. Their ability to penetrate existing defense systems raises concerns about the vulnerability of critical infrastructure, command centers, and carrier strike groups, potentially destabilizing regional and global power dynamics. The speed of hypersonic missiles compresses the decision-making timeframe for defenders, increasing the risk of miscalculation or escalation. This compressed timeframe, coupled with the difficulty of tracking and intercepting hypersonic weapons, creates uncertainty and can potentially lead to unintended consequences. This necessitates a re-evaluation of strategic doctrines and the development of new protocols for managing crises in the hypersonic age. The proliferation of hypersonic technology further complicates the strategic landscape. As more nations acquire these capabilities, the potential for miscalculation and escalation increases. This underscores the importance of international dialogue and cooperation to establish norms and regulations governing the development and deployment of hypersonic weapons. The emergence of hypersonic weapons represents a paradigm shift in warfare, ushering in a new era of strategic competition. Addressing the challenges posed by these weapons requires a multifaceted approach, encompassing technological advancements, diplomatic initiatives, and a reassessment of strategic doctrines to ensure stability in a hypersonic world. Section 6 Conclusion: The Future of Defense in a Hypersonic World. The Zircon missile, a marvel of modern engineering, embodies the disruptive potential of hypersonic technology. Its speed, maneuverability, and stealth capabilities challenge existing defense systems, necessitating a fundamental reassessment of defensive strategies and the development of counter-hypersonic technologies. The advent of hypersonic weapons marks a new chapter in the evolution of warfare, with implications extending beyond the battlefield. It prompts a re-evaluation of strategic doctrines, necessitates international cooperation to manage the risks associated with these weapons, and underscores the importance of technological innovation in maintaining defensive parity. The future of defense in a hypersonic world hinges on a multifaceted approach. This encompasses investments in cutting-edge technologies, such as directed energy weapons and advanced radar systems, capable of detecting and intercepting hypersonic threats. It also entails the development of new defensive tactics, leveraging artificial intelligence and machine learning to enhance situational awareness and accelerate decision-making processes. Moreover, fostering international dialogue and cooperation is crucial to establishing norms and regulations governing the development and deployment of hypersonic weapons. By promoting transparency and responsible behavior, the international community can mitigate the risks associated with these technologies and ensure a more stable and secure global order. The hypersonic age presents both challenges and opportunities, and navigating this new era requires a comprehensive and collaborative approach to safeguard global security.